Okay. Uh, good. Good morning, and let us start the course. And
Right.
the course, whatever I have designed, is basically will be introduction today. I will just go through a normal or a general knowledge type of seismological things, which mostly everybody knows, and then gradually we will be going to the deep. Okay, so each and every things will be explained much more details and much more rigorous way, so that you can do some in future research or work or something like that. But first of all, today mostly I will be dealing with a normal or a general type of seismology. Okay, so this is the my introduction. I am a professor at the College of Engineering at the University of Alaska, Anchorage. And so today's lecture is basically the introduction, the internal structure of the earth, seismic waves, measurement of earthquakes, and a little bit on the world seismology and a introduction of the hazard. Because the hazard is a very big topic, I will not discuss in a 1 or 2 slides with the entire part of the hazard, but the hazard will be coming in future courses, and it will be much more in details. Okay, so first is the introduction is basically the seismology. So seismology is basically comes from the word seismos, and it is called shaking. Okay, so it is a Greek word, and you all know the logos or the logi, just in biology, all the logos means it's a study or it's a science. So, so basically, the seismology is a science of shaking. So that's the basic difference. And when basic the information, the study of the shaking of the earth. Okay. Next is the seismology. Is the branch of geophysics. Of course, it is a concern with the study and analysis of earthquakes, science of energy propagation through the earth blast. So that's the seismology part. In a very nutshell, seismology has a very main scope, big things, but that's the actually we do not only explore the earth blast. We, by seismologists, are also in going to get the information about the mental, mental quality, all sorts of things. And there is and the engineering seismology is the concern with the solution of engineering problem connecting with the earthquake. So if there is an earthquake happens, there are a lot of concern in other things. So basically, engineering seismology is dealing with that. Okay? So study of earthquake gives us an important clue about the Earth's interior. That is our seismological point of view. And the understanding of the earthquake is actually help us to minimize the damages, the losses of earthquake, take money losses of life during the earthquake. Now, in this topic, I do not know but can we stop? But can we stop me and ask the question, or one day for this, for a special session, anyone? Yeah, for me it is fine, because if you can ask the question in between, that would be much more interactive way than to keep everything in the last, because then I will also forget in the weak sense I don't take on it toward that. So you can always stop me if you have any question. Okay, so the goal of engineering seismology is what is the scientific explanation to damage or the lack there of in the structure. So we have the engineering building code that has been developed over the years, and each the edition of the building code take the data from the previous earthquakes, and then they had improved that the on the building code and the lack in the structure, lack in their design things, So that will be improved by the earthquakes information we have received, and during the big earthquakes, and with the presence of the lot of seismic sensors all over the earth, we have a lot of informations now. Earlier, the most of the sensors or the most of the data are only accumulated at the California or the west coast of the United States. But now, a lot of the sensors or earthquake strong motion sensors, we call it, are all over the earth, and every places which are very earthquake prone area, we have lot of sensors and lot of data are accumulating, and as a result, our informations from a particular earthquake are now too much, and now particularly in the earthquake prone areas. So we are trying to improve the version of our in the international building code, and also the US building codes are being tremendously improved. So that's earthquake is giving you that opportunity. And we also try to know, or the engineers also try to now understand what are the characteristics of an earthquake. Earlier, the earthquake was treated as an earthquake. Now the earthquake is being treated as a rupture propagation. What is the directivity of the earthquake? What is the type of the faulting? Now engineers also understood all these things and try to do the building generation based on these information. So these are basically gives us the added information to the building design. So and we also try to understand what is the seismicity of a regions, and what are the types of the earthquakes are being expected in that region. These are also informations. Now the problem is this, that the most populated areas are the center of the most devastating earthquake. If the devastating earthquake occurs in an area where there is no people lives, so then there is not a very big concern. But our big concern is that when I name the most populous areas in the world, and that area is also a seismically very active zone. Say, suppose in a Japan, suppose in a Alaska, in some part of the Alaska, suppose in a California, suppose in a Turkey, suppose in a all these places. Say, suppose in a north, our Indian north, east, Himalaya, the northwest Himalaya, central Himalaya, all are the populous area, and there is a possibility of the big earthquake. So therefore, and most of the areas, the building codes are not truly followed, and there is a lack of population, lack of construction practices, and as a result, the problem get aggravated. Okay, so that we need to understand. So seismology is the sharing point of the roadmap to seismic security. So that's the biggest word, is the seismic security and how we achieve it. So understand the hazard is one of the main part. What is the earthquake hazard associated with that particular area, and designing a proper building code based on that, and implement it through the government, that building code for the construction of the structures or the bridges, or building or bridges. These are the very important things. Retrofit of the old structure, although it is a very, very good to say, but it is very difficult to achieve. At least also in a country like US, the retrofitfication is a very big problem. It's not a very easily solvable problem, as we can say, but that is also we could do if we have a more information about the things, and also the prevent the non-structural damage. Sometimes the structure didn't have a very big problem, but the non-structural elements, say suppose these lights and all these things on the fans and all other materials, they got seriously get damaged. Say suppose the water pipes and these things, so the building gets flooded. And also, we need to develop a very uh, response system of an earthquake, because during the time of an earthquake, the people need to give the information to the masses. So there is in US we call it as the shake map. So that means as soon as there is a shaking, within few minutes, a shake map will be prepared, and that has been circulated to the emergency operating centers of that area. And then emergency operating centers can clearly show which area might have been caused more damage compared to the other areas. And so the emergency responder can concentrate on that area, try to save as many as life as possible, right? So these all the things can be developed with the engineering seismology point of view, right? So a seismologist, as a seismologist, we all study the earthquake source, the seismic wave propagation, and the geological cause of these seismic waves, the sources of the artificial sources of the seismic wave, ways to determine the earth structure from the record of the natural and artificial seismic waves. So we are all try to understand the structure of the earth from these earthquake studies by doing a 1D, 2D, or 3D modeling. So that's the main part. And also we try to understand how the seismic wave, when propagate through the earth, get attenuated. So basically all the inelastic and elastic attenuation model we will be studying, and also the seismic hazard analysis is a part of the study too. So next question is a very big question, and this is the most fundamental question, and everybody try to have an answer, that what is an earthquake? So earthquake is a vibration of the earth produced by a rapid release of accumulated energy in a elastically strained rod. So that a strained rock. So basically the rocks are already been strained due to the force on the rock, and for a geological time, and then it was already strained, and after that the rock cannot hold that much of amount of energy. We will be all doing the mathematical details of these things afterwards, but then it will all starts releasing, and we call it an earthquake has happened. More amount of energy stored into the rock for a long geological periods, that more energy will be released, right? So the point where the energy released are called the focus or the hypocenter, and energy propagates in terms of seismic waves, and the instrument which record is called the seismometer. Okay, so these are all informations, and you all know, I know that, but just a recapitulations of the things. So this is the one of the common picture. You can find it in any of the internet. This picture says that this is your focus of the. Can I share? It's like invisible, right? So this is the focus, and the epicenter of the earthquake just vertically above is the epicenter, and this blue line is basically the fault on which this earthquake has happened. And this blue line is actually this surface trace of the fault. So that means on the surface, if you project it, so then this is your surface stress, and this is the entire part is the fault zone, and this is the epicenter of the fault. So epicenter is a part of that fault zone, and we keep this image in our memory, so that in future, whenever we try to model the seismic wave propagation, we all use this as our basic modeling. Okay, so this is your distance. So this distance from the epicenter to this distance, we call it as a epicentral distance. And this distance this is where the recording stations are, and this distance we call it as a epicentral distance, and this is what we call it as a hypocentral distance. Sorry, this color is a different. So it's a hypocentral distance, and this is your epicentral distance, and this is the recording station. This is the earthquake, right? And this is what we call it as a focal depth of an earthquake. And we will be coming to these pictures, and we will be defining different type of depth in future. But focal depth is one of the easiest way of understanding the earthquake depth of the depth of the location in a 3D in the underneath the structure, right? Now, so earth structure is mostly, it is a dramatic variation we have seen is on the radial structure, right? So that means from the earth, from the center of the earth to the surface of the earth, the variations we assume is on the particle structure. The laterally there is definitely a variation, and we will discuss on that, the lateral variation, but the modeling we are more interested in our particle structure modeling. Okay, the radial, there is a heterogeneity, but that heterogeneity we will be addressing on a different parameter, just like what we call it as a site response and all these things. Okay, so now Earth can be divided based on the chemical behavior and based on the mechanical behavior. So there are two behavior Earth structure can be divided, and the mechanical behavior is basically, we call it as a lithosphere, asthenosphere, mesosphere, outer core and inner core. And from the chemical composition point of view, it's the crust, mantle and core. So that we all know that. Okay. So crust is a most heterogeneous layer in the Earth, and it is most poorly described by the radial models, because all the problems, whatever we had seen, our structural losses and everything are mainly on the not understanding the crustal part of the Earth. Mantle and the core mantle are more or less, we all know its heterogeneity is not that big to discuss about, but the crust heterogeneity is very is basically varying too much from one point to the other point, and that is what we have to understand. So crust average thickness, so that means the continental on a continental side, it is 33 kilometers, and 10 kilometers is beneath the ocean. So the ocean, it is only the oceanic crust, and in a continent we have a granitic crust as well as the oceanic as well as the basaltic crust. And so crust sometimes underneath the mountain underneath the Everest, it is something around 70 kilometers thick. So the 33 kilometer is an average. It could be as large as 70 kilometers also. Okay. Any question up to this much? Everybody's okay? Okay. So I think these are all general knowledge for you guys. So the shallowest layer is called Earth, and the next part is the mantle. We call that boundary is a Mohorovicic discontinuity, or we simply call it as a Moho boundary, and that's a very important aspect of our seismological study. And we will take care of this part in our data analysis, and whenever we do the any analysis of the earthquake data, we always talk about the Moho reflection or the reflection or the refraction from the Moho, because there is a velocity discontinuity is too much from the from the lower crust and the upper mantle. So, um, so there is the outer core also. This is the innermost part, and the outer core is more or less uh, a liquid part, and and the inner core is a solid material, right? So that outer core is a liquid that also creates a lot of seismological phases, but to be present and not present onto the certain places depending upon the earthquake location. So that also we will be doing that, right? So Earth's outer core is the radius of the outer. Oh, sorry. The radius of the outer core is known to be 3 to 4 kilometers, and 3480 is basically the radius, and the boundary between mantle and outer core is very sharp boundaries, and we call it as a CMB boundaries, or the core mantle boundaries, and that is also we need to look after. And the inner core is a purely iron, and it is basically a solid material, right? So with this, we will be seeing that these are the mechanical properties. That means the outer core, inner core, the mantle, and the crust. These are the mostly the mechanical part. And then we have a three different mechanical layers, which is the lithosphere, asthenosphere, and the mesosphere. So we will be coming to that picture very clearly. I do not know whether I can show it to you here. So up to the 110 kilometers from the, or 100 kilometer on the thickness of the earth crust, we call it as a lithosphere, right? So the lithosphere is a material which is a 110 or 100 to 110 kilometer thick, right? And so this will float on a upper mantle side, which we call it as a asthenosphere, and that is basically our mechanical model, right? So let's see if I can go for a little bit. So if you can see, this is your white, a small strip. This is your lithosphere, and it is a cool and hard rock. And then asthenosphere is a weak and soft rock. It is underneath. It is underneath the gray part of the material, and then there is a mesosphere, which is the dense and the rigid rock. This is your mesosphere part, right? And then there is a outer core, and then there is a inner core. Outer core is a liquid, inner core is a solid. So this is our part. So whatever we call it as a plate or plate subduction and everything, these are dealing with this all the lithosphere part. Okay. So if you can see from the side that this is basically the continental side, and the continental side, the thickness is around, as I said, the average thickness is 30 kilometers. Average thickness is 30 kilometers, but it could go up to 60 or 70 kilometers. So this is the continental crust, and then it gradually on the ocean side, it becomes, this crust is a totally basaltic crust, and then it is the lithosphere, which is basically 110 kilometer to 120 kilometer thick. So this orange line are the lithospheric material, and this will be on the ocean side. This will be around 50 kilometers, and after that, these are the asthenosphere. So based on the mechanical property, this is the part, and then we have defined this is the water, and then the continental shelf and the sediments. During the time of discussion on the subduction, we will talk about this part. Okay. So when do earthquakes occur? So the main answer is earthquake either occur in the fault or on the plate boundaries, right? So our plate boundaries in India is basically the Himalaya, where the these our Indian plates subducted under the Tibetan plates, okay, and that's the Himalaya part. So all of the on the continent and the ocean continent boundary, we have seen some of the subduction, and these subduction zones are basically the biggest source of the earthquake. Earthquake also do occur in the fault. Say suppose in America there is a San Andreas fault, which is in the North America, or in the continent. Say suppose Anatolia fault in the Turkey. These are all the surface features or the surface earthquake or intracontinental earthquake. So that we also see some of the not that big earthquake, but the 7.5 earthquake is more or less common in the fault zone, right? So that tectonic plate we all mentioned about, these tectonic plates are basically floated on the asthenosphere, right? So that's the main part, that the tectonic plates are floating, and as a result, it's moving because the heat convection underneath this asthenosphere actually drives the upper tectonic plate, and as a result, the plate subduct underneath the continent or underneath the ocean. Oceanic plate subducted underneath the continental plate, and these things are occurring continuously, right? So it is not that it is not occurring now, it is occurring in some part. It is not that. It is a continuous process, and by the process, some part of this subduction is getting locked, and when there is a lock, then there is a possibility of the energy generation, and that energy goes on accumulated for over the years, and after certain time it get basically released all the energy, and as a result we can see there is an earthquake can happen, and these earthquakes are very devastating earthquakes, those which are coming from the subduction zones, right? Okay, so so the plates are basically a part of just like your boiled egg. If you can take out the boiled egg or one of the cell, then that is basically a plate, and that plate, as I said, it could be 100 kilometer thick, the lithosphere plate, and it's floating on a mantle, which is the asthenospheric material, and this is what is the basis of this things. And this part you can see, this is your what is called, anybody knows this part, this entire these red dots? What is this red dots? This is the ring of fire, and this ring of fire is located on all the sides of a continent, and these water bodies we call it as a Pacific plate, and on the top of it is the North American plate, and so this is your Japan plate and the Philippines plate. So there is a lot of complexity is there in the Japan trench. There is a Philippine plate, there is a North American plate, there is a Philippine plate. They are all this. Then there is a New Zealand plate, and these are all the earthquake. And we are just now plotting in this plot. Possibly they had plotted last 100 years of seismicity, right? But in the continent side, there are some of the earthquake has happened. See, suppose on the top, when there are some earthquake inside the US, there are some of the continental earthquake. These are not associated with the subduction, but this has a totally crustal fault areas, right? So based on that, we have a African plate, the South American plate, North American plate, and then all the plates we can show it here, right? So 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 basically, what drives the plate movement? It is nothing but the 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 hotness inside inside basically the mantle material, which is hot, and it sets up a convection current, and due to this convection, there is a rifting occurs, and through that rift, which we call it as a mid-oceanic ridge. But should I continue and take it? The rifting and the subduction zones happens, right? So this mantle, let's say, switching about issues. So this is your picture. So this is your mantle, and this mantle material come up through the mid-oceanic ridges, and then there is both the sides, the lithospheric plates are being subducted, and this subduction goes on, and then it goes back to the mantle itself, the part of this, and these things continued for the entire cycle is continuing, and this is your subduction zone. And if there is a subduction, then also you can see from here, there is a in that like this. So when you use so as soon as there is a subduction, you will be definitely seeing when there is another part of the process is called the volcano. So all of the subduction zone area, wherever the plate is subducting, you will be definitely seeing a presence of a volcano, right? And some of the active volcanoes are all located also on the your ring of fire areas, right? So in the mid-oceanic zones or the mid-oceanic this area, we have a divergent plate boundary. So the plate boundaries are basically spreading from this area, and on the subduction zone, this is the convergent boundary plates, and on this mid-oceanic region, and there is another mid-oceanic regions in between. This is basically a transform fault. So this is the transform fault. This is the divergent plate, and in this side there is a convergent plate boundaries. Okay, so this is a divergent or tension, where all two plates move apart. So this is an earthquake. There is a magma coming out, and there is a divergent plate boundaries, and this is the convergent or the compression type of things. So if you can see it is in a plate, then this will be the convergent or the compression things, and then there is a transform or the shearing fault or the shear fault is in the transform fault boundary where two plates are slide past each other. This can be also seen in the crustal faulting. Also, we can see the shearing of the two sides of the fault, right? So that's a transform fault. So a tension fault, compression fault, and the transform fault. These three types of fault we can discuss in our next slides or the next classes, and how they are to be related with the much more details. So the convergent boundaries, this might be a ocean and the continental boundaries, right? So which boundary, if there is a ocean and continent, which boundary will be subducted? Why? is basically much more denser than the continental part, right? So that's your and this is your this part, and then the Himalaya region. We had seen that there is a continental part of the Tibetan plateau is also subducting. Right? The Indian plate is subducting under the continental plates, right? So that is a in that case, we decide that which plate is a lighter in the material than the other part. So the Indian plate is much more lighter. So that is why it is basically subducting underneath the Tibetan plate. Okay. So now these are all like what the plate boundary part, and then fault part. We also need to know from the geologist that all the faults, first of all, we need to understand are not active, right? So it doesn't mean that if there is a fault, that fault can generate seismic event. It may not be, because some fault are a seismic fault. So that means that fault is although there, but it cannot generate the seismic activities. But some fault are highly active seismic fault. And which one is seismically active and which one is not seismically active, it's basically very difficult to say. We have been fooled by a lot of times that we thought some fault might be non-active, but it was basically it has created devastating earthquake.